We're Team 9. My name is Ben Huff.
My name is Anne Linden Griffin.
And my name is Sarah Karima.
And my name is Greg Smith. We will be presenting the Embedded System Design Project for the spring 2017 semester.
This project consisted of putting together and programming 4 rovers to play a game of Capture the Flag. Capture the Flag is a game where one team tries to get a flag without getting tagged from the other team. The project requirements consisted of having a sensor rover, which is the purple arrow. It will go from left to right, scanning for obstacles and rovers on the playing field. The flag rover, which is the green arrow, would receive a map of objects from the sensor rover and find a path to the flag. The tagger rover, which is the pink arrow, would receive a map of objects from the sensor rover and find a path to the other team's flag rover. The countermeasure rover, which is the yellow arrow, would receive a map of objects from the sensor rover and find a path to the other team's tagger rover to try to distract them from tagging our flag rover. These rovers communicate wirelessly through small devices called Wi-Flies and the server that is able to route the messages that the rovers send and receive. Now we are going to go through our individual contributions to the entire project. Due to the fact that we are not able to integrate, our final demonstration for our project consisted of a GUI and a client to act as the other rover or rovers. The server is written in Python and set up on a Raspberry Pi. The server is the central hub of communication. It would essentially route messages. It would get the IP address of the message it receives to determine the destination of the request or response. It would then route the messages to the correct destination to tell the rovers what to do. Next, I will discuss the sensors that I worked with. I configured infrared sensors and a reflectance array sensor. The infrared sensors were used to determine how far away objects were. The communication to the PIC MX32 was done through the ADC. The reflectance array was an array of 8 infrared sensors that was used to determine if there was tape or not. Communication to the PIC MX32 was done through the ADC. Although not perfect, this sensor was able to detect the difference between tape and non-tape.
Here we have the Graphical User Interface, or GUI. This control hub allows us to control the state of the rovers, request information, and debug outputs. The GUI uses the same JSON communication schemes as the rover, and works really well for debugging and unit testing. In addition, I also made a map editor that could be used to generate maps with obstacles and rovers in order to test the map-dependent rovers. This was a large part of my contribution to the project since it could be used by 3 of the 4 rovers, and improve the quality of our tests and decrease the time needed to test. Some improvements that could have been made include incorporating a Save Map button for when we design a good map. Other minor improvements include more network error handling and reconnecting to the server when it crashes.
The motors operate using a motor shield that connects the 2 motor encoder chips to the microcontroller. The encoders use a digital pin to control direction, and the speed is controlled by oscillators in the microcontroller. Changing pulse width modulation values of the oscillators changes the speed of the motors. A 3rd pin on each encoder is used to get feedback values for the PID adjustment system. A motor task was designed to control the motors by accepting struct messages from a queue. The struct contains a message type character, which can be used to identify the message as an encoder value, a motor instruction, or a stop, go, pause message. These messages are used to adjust the motor speed, instruct the motors to go certain directions and distances, and stop or start the motors. There's also a proportional integral differential feedback loop, a PID loop, which adjusts motor speed based on current speed. The feedback loop accepts encoder values and calculates an adjustment value for a proportional, integral, and derivative equation. These values are then summed up and converted to a meaningful pulse width modulation speed that is passed to the oscillators.
JSON formatted messages are essential to the communication system. To accommodate writing and parsing JSON messages in the JSON task, we use JWrite for JSON packaging and Jasmine for parsing. The ultrasonic sensor was intended to provide better accuracy of the flag's location. It is able to see an object between 30 to 5,000 centimeters away from the sensor. The PixieCam helps identify the flag by sending a signal to the PIC MX32. if the flag is in its field of vision. We used CMU-CAM5 Pixie Plotting Guide on cmucam.org as a guide to enable communication between the PixieCam and the PIC MX32. The communication between them is done through a UART interface.
Here's our sensor rover. It shows two sides, one that contains the sensors mounted on a 3D printed material, and the reflectance array sensor that is attached at the front of the rover. The sensor rover consisted of two infrared sensors, as mentioned before, and a reflectance array sensor. Even though the reflectance array sensor was able to distinguish between tape and not tape, it was not able to follow a straight line as it was supposed to in the project requirements. This could have been improved by being able to read more infrared sensors from the reflectance array sensor and determining a good threshold for tape or not tape. Something that could have been improved as well would be able to see a difference between a sensor that sees the edge of the tape, a sensor that sees a central piece of tape, and a sensor that doesn't see tape. This rover communicated through the Wi-Fi and server to generate a map of the objects that it sees from the sensor. Overall, the sensor data from one of the sensors was not great, so it was not able to distinguish between rovers and obstacles. This video shows the sensor rover in action. As you can see, the sensor rover moves up and down the field to scan for objects. The IR sensor would have to convert its raw data into a centimeter value to determine the distance. The way this was calculated was by getting numerous samples and plotting a best fit line to the data. This would store the data in an array of obstacles with X and Y coordinates. The X coordinate was based on the sensor readings, and the Y value was calculated based on how far the rover moved from the starting position. When the rover receives a request from the client, it will send a long list of obstacles in JSON format, and the client will then create a map of the obstacles. As you can see, the green line shows the path of the sensor rover, and the blue and red filled boxes show where the obstacles are seen. The red is the view from the upper sensor, which is therefore inaccurate because it sees something that doesn't exist. The reasoning for this could be that the sensors were lined up in a way that they interfere with each other, or it saw wires or other things when moving across one of the tabletops in the lab area. This was something that could have been improved.
Here is our countermeasure rover. Its sole purpose is to be an annoyance to the enemy team by charging towards the enemy tag rover. Unlike all the other rovers, the countermeasure rover starts in the enemy defense zone, not our own. This allows us to disrupt the enemy tag rover when their flag rover isn't around. When it is, there are an additional set of restrictions that prevent our countermeasure rover from moving. We had originally intended the countermeasure rover to run interference with the enemy sensor rover with infrared and ultrasonic emitters, but the emitters that we ordered didn't come in. Instead, we ran full defensive tackle mode, which is football terms for protect our own offensive rover, the flag rover. This means that we want the countermeasure to do whatever it can to get in the enemy tag rover's way, so it can't safely get to our flag rover. This was done using the A-star pathfinding algorithm I implemented earlier. Here we see the map that the countermeasure rover is playing on. It's going to attempt to get to the tag rover by going south, but then hits tape and changes the direction. It then proceeds to navigate around the obstacle, making the appropriate turns until it reaches the enemy tag rover. This has been tested with updating the map in the middle of the path, as well as changing the location of the goal. Some improvements that could have been made would be playing around the flag rover, for instance, posing as an obstacle, or identifying a blockable path and acting like a door, but only for our rovers.
Next is the tag rover. The tag rover has a push button, an LED, and a line reflectance sensor array. The tag rover's goal is to prevent the enemy flag rover from getting into the flag zone. It is supposed to tag the flag rover after the flag rover has entered our team's defense zone. In our original project requirements, we planned on having the tag rover pace back and forth in front of the flag zone. However, we diverted to waiting in front of the flag zone instead. Here is an example of the tag rover in action. In the video, the rover begins by waiting for a go command from the GUI. After it has received or requests a map, finds a path, then sets off towards the closest coordinate in the enemy flag rover's path outside of the flag zone. When it hits tape, it blocks off that part of the map and recalculates a path to avoid the tape. Once it gets to its destination outside of the flag zone, it orients itself north, then determines whether the enemy flag rover is in the defense zone. In this particular case, the enemy flag rover is in the defense zone, so the tag rover tracks it down and tags it. Once the rover has successfully tagged the flag rover, it stops moving and the LED lights up, indicating a tag. The push button can be unreliable at times, causing it to randomly indicate a tag where there is none. Other than this, the rover should continue receiving maps and chasing down the flag rover indefinitely. There were several improvements that could be made to the tag rover. The button sticks out far and can potentially hit objects. This can be dealt with by changing the physical design of the rover or giving obstacles a cushion space in the pathfinding. The tag rover does not take into account enemy countermeasures. It is very susceptible to countermeasure rover interference. Finally, there is nothing in place to assure that the enemy flag rover was the thing being tagged. This could be changed by checking to assure that the tagger rover did meet its goal.
We will now discuss the flag rover. The flag rover's main task is to acquire the flag located somewhere in the flag zone. The flag rover is equipped with a reflectance array sensor, a pixie cam, and an ultrasonic sensor. The flag rover receives a map and follows a path generated by the pathfinding algorithm. It assumes that the goal, which is the end of the path, is somewhere in the flag zone. The flag rover then rotates in place until the pixie cam recognizes the flag in its field of vision. When the pixie cam tells the PIC MX32 that it sees the flag, the rover will move towards the flag until the pixie cam doesn't see it anymore, at which point the process of identifying the flag starts all over again. The flag rover is able to move through the field, identify the flag, and chase it. However, the flag rover is unable to correctly detect the tape and would go over the field boundaries. We also were not able to implement a mini gripper that can grab the flag and drop it outside the flag zone. Instead, the flag rover will attempt to push the flag outside the flag zone. This process is rather unpredictable and can consume a significant amount of time. To improve the flag rover, we can re-implement the tape detection sensor. A way to do this is by implementing different sensors, such as a color sensor. Another improvement we can make is the flag acquisition. A more capable and reliable flag grabber, such as a mini gripper, would be a great improvement over trying to push the flag outside of the flag zone.
Thank you for watching our video. Overall, all of our rovers have the capability to run forever even though we are not able to integrate them together.